Hi, everyone. So in the last couple sessions, we've talked about this Big Bang theory, the idea that the universe is expanding and cooling, and that earlier on in the history of the universe, it had this hot, dense state, and then went through all of these transitions between these different eras to go from a universe in this hot, dense state to the universe that we see around us today. And at the time, there were, some reasons to think that this might be a possibility. We had Einstein's theory of general relativity, was developed by Einstein and kind of published in 1915 and 1916, which showed that, well, the geometry of space and time can and will change over time. So there was a mechanism for this expansion. Observations had been starting to be made about more of the large scale structure of the universe, this cosmological principle that on large scale there's no special locations and no special directions. That's that the universe is on very large scales homogeneous and isotropic. And Hubble had started measuring the redshifts of these galaxies, noting that all distant galaxies are redshifted, and the further away they are, the faster they are moving away from us. They seem to be moving away from us. And this kind of an expansion is characteristic of what would match a universe that is actually expanding. In fact, going back to Einstein's theory of general relativity, when Einstein was looking at his own equations for general relativity and trying to apply them to the universe, he noticed that the equations had kind of this imbalance to them where the universe itself would either start to expand and start to contract. And Einstein proposed this idea called the cosmological constant as a way to try to balance out that effect of, the universe might expand or might contract, introduced this kind of correction term to balance out the universe. And he later said that this was his greatest mistake because his equations ahead of time were suggesting that the universe should be expanding or contracting, which would have been able to predict some ideas of Hubble's law. In fact, it was another physicist and actually ordained priest by the name of Georges Lemaitre, who had looked at Einstein's equations and suggested that, these equations suggest that the universe could have started in this small state and expanded from there. I think he called it the cosmic egg or something like that. So again, there was some pretty decent reasons to think that, well, this model might actually describe the universe. But it was not enough for a lot of astronomers and cosmologists to go from, we see some of these patterns in Hubble's law, to this whole idea, this entire package idea of the Big Bang Theory. So again, this Big Bang Theory, it suggests that the universe's history has been a history of expanding and cooling, going through these eras where forces separate, matter clumps together, and then eventually we get atoms coming together into galaxies and the kind of universe that we see around us. And again, in order for something to be a scientific theory, that theory must make testable predictions of nature, and we have to have put those claims to the test and see that it passes all of those critical tests. So in order to really be able to say whether we think that this Big Bang model is actually achieves the rank of scientific theory or not, we're going to need some more evidence. Now, before we do that, let's just briefly kind of talk about this timeline just in very, very general terms. So we've got these different eras: the Planck era, the GUT era, electroweak particle, era of nucleosynthesis, era of nuclei, and era of atoms. So, and the approximate times of when these things occurred. So let's briefly talk about these. In the first couple eras, the Planck era, the GUT era, and the electroweak era, that's basically when all of the forces are separating. We know basically nothing about the Planck era. The GUT era, we have some models of what we think physics might look like in that situation, but we probably need more data to gain more a higher level of confidence. Electroweak, we're actually able to test in particle accelerators today some of the properties of physics right near that electroweak era. So we can actually put that part to the test. Again, that is still only 1/10 billionth of a second after that first Big Bang event. Moving on, in the particle era, we have matter and antimatter. We have quarks starting to come together to form protons and neutrons. By the end of that era, we have matter starting to clump together. There's no more antimatter and no more free quarks. During that era of nucleosynthesis, we've got, in the entire universe, we've got hydrogen fusing into helium. But within a few minutes, the temperature of the universe will have gone down enough, the temperature and density in the universe will have gone down enough that fusion is basically going to stop, leaving us with a universe of 3/4 hydrogen, 1/4 helium. In the era of nuclei, we have all of these nuclei of hydrogen and helium flying around and a whole bunch of free electrons. And those free electrons make the universe opaque. Light loves bouncing off of free electrons. But eventually, after around 380,000 years, the universe finally reaches a low enough temperature that neutral atoms form. So all of those free electrons that were flying around get captured by those hydrogen and helium nuclei. No more free electrons means that the universe is now transparent. But again, in order to take this timeline, we want to say, does this timeline make any specific predictions that we can go out and test? So that's what we're going to be looking at in these next couple of sessions. So for this first one, we're just going to look at, in general terms, some of the overall lines of evidence that we have. So one of the lines of evidence comes from this event right here, when neutral atoms formed. We said in this Big Bang model, around for the first approximately 380,000 years, the universe was opaque owing to the presence of these free electrons. And again, photons love bouncing off of free electrons. But once neutral atoms form, those photons that were bouncing around off of all of those free electrons, they're going to bounce one more time, and then they can travel through the universe unimpeded. That light that was bouncing through the universe and then hit one more time, and then the universe became transparent, and now that light can move freely through the universe, we can still see that light. Oh, sorry about that. That last scattered light has nothing to block it, and now we can actually see this light, though it is extremely redshifted. Remember that as the universe expands, those wavelengths of light are going to stretch. So this light that was last scattered at the end of the era of nuclei, and then the era of atoms starts, and that light can freely move through the universe, that light is still around us today. We call this the cosmic microwave background, or the CMB. We're going to have a whole separate session devoted to talking about the properties of this cosmic microwave background and how this was one of the huge confirmations of the Big Bang model. It predicted this light, and then a separate group of astronomers a separate group of scientists kind of accidentally found this light while a separate group was going through the predictions and getting ready to look for it. But again, we'll talk about this cosmic microwave background in quite a bit more detail a little bit later. So again, we can literally see the afterglow of the Big Bang, but again, it's highly, highly redshifted at this point, so we can actually see that afterglow. There's other lines of evidence. Going back even further, we have this era of nucleosynthesis, where hydrogen, those free protons, were starting to fuse together to make helium. And this was, again, going on throughout the entire universe. And the model of this Big Bang theory makes very specific predictions that by the end of this era, the resulting universe should be made up of pretty much 3/4 hydrogen, 1/4 helium, and again, a couple of extremely, extremely tiny trace abundances of lithium. Well, when we look at very, very distant gas clouds, clouds that have not gone through this star-gas star cycle, either because they're very isolated in space or because these gas clouds are so far away and we are looking so far back in time, we're actually looking back to the eras before the star-gas star cycle and earlier generations of stars had actually been able to produce more of the heavy elements on the periodic table. So again, this Big Bang model makes a specific prediction of how much hydrogen and helium should be present in the early stages of the universe. And when we look at these distant gas clouds, that matches. So that gives us a way of testing our understanding back to the first couple minutes of the Big Bang. So let's try a question based on this. Which of these abundance patterns, if detected in a star or gas cloud, would constitute evidence against the Big Bang model? Pause the video and try to think through this particular problem. Okay, so let's go through some of these ones and see which of these would constitute evidence against the Big Bang. Because remember, in any scientific model, it has to be falsifiable. There has to be some observation that we could make that if we made that particular observation and got that particular result, it would disprove our idea. So what would be evidence against the Big Bang model? Well, this first one, let's look at this first one. We have a little bit less hydrogen, a little bit more helium, and a little bit more heavy elements. Would that be evidence against the Big Bang model? Do we know of any ways of converting hydrogen into helium and heavier materials? Well, we know that stars do this regularly. We have a mechanism where significant quantities of hydrogen can be converted into helium and the heavier elements. That's the star-gas star cycle. For this one too, well, we've lost a little bit of the hydrogen, gained a bit of helium, and some of those heavy elements. Well, that's also could be explained by having gone through the star-gas star cycle, but just not as much through the star-gas star cycle. Maybe this is a gas cloud that is a little bit older, but not super new. This would be the newest material. This one would be the oldest material. So basically only hydrogen, only helium, and barely anything else. That would be really old material. This one would be kind of partway in between. So partway through that star-gas star cycle. However, for this one, for this composition, we have a lot of extra hydrogen and way less helium. Do we know of any large-scale mechanisms that will take significant quantities of helium and break it back into hydrogen? Do we know of any naturally occurring systems that do that? Not really. We don't really know of any large-scale mechanisms that would tend to convert helium back into hydrogen. So if the universe is supposed to have essentially started as 3/4 hydrogen, 1/4 helium, again, after this era of nucleosynthesis, we don't know of any way that we could get a gas cloud looking like this. If this was ever detected, it would be a significant problem for our Big Bang model. It would go a long way to acting as evidence against the Big Bang model. So again, this is a falsifiable theory. There are observations that we could potentially make that would falsify the theory. If we ever found this, that would be really, really difficult to explain. But try as we might, we have never detected a cloud of gas in space that has this particular composition. In fact, we can go into even more detail. I mentioned that the universe, after the era of nucleosynthesis, was about 3/4 hydrogen, 1/4 helium, and nothing else. Well, we can even look at some extra little elements, because also in the Big Bang, it would have produced a tiny amount of deuterium, which is an isotope of hydrogen. It would produce a tiny bit of helium-3, which is an isotope of helium, and also just a minuscule amount of lithium-7. I kind of mentioned this a little bit more of that kind of trace of lithium produced in the Big Bang. Well, we can model how much stuff there is in the universe. So this axis is how much matter is in the universe. So the amount of matter. We're not going to worry about these units or what this is specifically saying. Essentially, this is if the universe was pretty close to being empty, not much matter at all, or if the universe has a lot of matter in it, it's much more dense. So this is saying if the universe had different densities, different amounts of matter in it, then this era of nucleosynthesis, how much hydrogen, or sorry, how much helium-4 should it produce? How much deuterium should it produce? How much helium-3 should it produce? And how much lithium should it produce? So if I found something where there was, let's say, this much helium-4, this much deuterium, this much helium-3, and this much lithium-7, so I couldn't draw a single vertical line matching up the amount of this material, that would again disprove my theory. However, what we do find is the amount of helium-4, the amount of deuterium, and the amount of helium-3 all match up with the Big Bang model exactly. And the amount of lithium-7, there's a slight discrepancy. This tiny trace of a trace is slightly different than what we would expect. Again, not much different, but there is a slight difference. This is actually referred to as the lithium problem. And it's an open area of research saying, well, is there any other physical mechanism that could have changed exactly how much lithium is produced? It's an open area of research. The error bounds on this are still pretty large. There's a large amount of uncertainty, not a large amount of uncertainty, but a little bit of uncertainty in are there any other mechanisms that could have produced or gotten rid of some lithium-7? But it's still a pretty close match for one and only one original matter density in the universe. So we can actually use this to measure how much matter is in the universe. We'll actually see this come up again a little bit later in the course. So again, we're making predictions and using that as a test of whether our observations, again, these horizontal lines are the actual measured abundances, whether those actually match up with our predictions or not. In this case, matches up very well. So the abundances match with predictions. Again, a couple of open questions about a tiny bit of extra lithium, but still matches up pretty well overall. What other lines of evidence do we have? We have the Big Bang model is suggesting that the large-scale structure of the universe hasn't always been the same. It seems like we started with this universe that was almost the same on large scale. So again, homogeneous, no special locations, isotropic, no special directions, but there were just certain areas that were slightly more dense than other regions. And the model predicts that those slightly overdense regions should collapse under gravity in certain ways. So we can run computer simulations of how would the universe have gone from this basically universe that's full of material with a few regions that are slightly denser than others. How do we go from that system to the kinds of structures of galaxy clusters that we actually see around us? We can also look at the time frame over which that happens. We've talked earlier in the course about how do we measure the ages of clusters of stars. when we look at the ages of clusters of stars and look at the simulated timelines for how long does it take for galaxies to form, how long does it take for these star clusters to form, how long has the universe been around for, the ages that we get for our oldest star clusters and the predicted ages for the age of the universe match up quite well. The abundances of these heavy elements, when we understand the properties of stars and that star gas star cycle where heavier elements are produced in greater and greater amounts, we know approximately the time frame for that. And we can match that time frame very accurately with the time frame that we get for the overall age of the universe based on the expansion rate. So the large-scale structure of the universe also gives more evidence in support of this Big Bang model. So again, in comparing surveys that we've done of what the large-scale structure of the universe looks like, what galaxies and clusters and superclusters of galaxies look like, how they distribute themselves, they closely match what is predicted by the Big Bang theory. So again, the universe's age as predicted by redshift and CMB calculations, we'll talk about that a little bit more later, again, is in good agreement with models of galactic and stellar evolution, the current abundance of heavy elements in galaxies. All of these timelines match up very, very well with each other. And this is all evidence in support of this Big Bang theory. So again, I'm hoping that I've given a decent case for, if we're putting the Big Bang theory on trial for being an accurate representation of the history of our universe, I hope by looking at the cosmological redshift, that galaxies seem to be moving away from each other in a way that is characteristic to what we would expect from an expanding universe. From the cosmic microwave background, this leftover light from the end of the era of nuclei and the beginning of the era of atoms, when the universe became transparent, that leftover light that we can measure. Looking at the abundance of primordial elements, so looking at some of the oldest gas clouds and saying, how does that match with what would have been produced, the elements that would have been produced in the early universe, and the large-scale structure formation. I'm hoping that this evidence will reasonably convince you that the Big Bang theory is guilty of being an accurate representation of the early history of our universe. So again, in the next sessions, we'll go into a little bit more detail of the cosmic microwave background radiation, especially, and talk about some of these other aspects of the Big Bang theory.